Hey guys, so in the last lecture we have seen three methods to find the natural frequency of any system. So the first method which we saw was equilibrium method, in which we used free body diagram to find the equation of motion, and through which, after comparing it with simple harmonic motion, we got the value of natural frequency. So, and so the second method was energy method, where we have added the total energy, that is kinetic energy plus potential energy, which is constant, and then we differentiated it and equated it to zero, because the differentiation of any constant is zero. Then we use the third method, that is relays method. So in this method we have seen that the both maximum kinetic energy and maximum potential energy would be equal, because when kinetic energy is maximum, the potential energy is zero, and when potential energy is maximum, kinetic energy is zero. So as kinetic plus potential energy total is constant, so therefore their maximum would be also equal to would be same. So using that principle, we have derived the equation of natural frequency. So today we will solve some examples based on that. So first example is, find the natural frequency of a simple pendulum. So to find this natural frequency, we will use both method, that is Newton's method or equilibrium method or energy method. So we will start with the first Newton's method. So before starting, I will draw a simple pendulum. So suppose this is the fixed surface through which a inextensible string is attached, having mass m and the length of string is L. So this is in equilibrium position, or this is in stationary position, it is not oscillating. So in this case, uh, there is no motion of there is no motion. So now suppose this pendulum is oscillating. So I will assume that, suppose this is the mean position, so it will oscillate from here to here. So suppose this is the extreme positions on the left and on the right. So suppose this extreme position is extending an angle theta towards the right. So suppose this is the extreme position, and the length of the string is L. So this length also will be equal to L. So let's calculate the forces on the system. So the first force of the bob will be weight, that is mg. It is mass into gravitational acceleration, which will be acting in downward direction. So similarly here also the weight will be mg, which will act in downward direction. Now as this string will also act some force. So this string will also have a tension in that string. So that tension force will, so suppose this tension force will be T. So opposite to there will be some force. So that is, if we divide this weight into left and right components, so we'll get the force. So suppose the left and the right component of weight, what it will be. So suppose this is the angle theta, so this will be W cos theta, and this will be W sin theta. So the tension in the string would be equal to W cos theta, so that forces are balanced. so that is T equal to W cos theta, but this W sin theta force is unbalanced. So this, according to Newton, there is equal and opposite force to each and everything. So this force would also be balanced, W sin theta. So so this force would be balanced with the help of this fixed, so this fixed support will be in opposite direction. So this this force, this two equal and opposite force will create a couple. So now this couple also need to be balanced. So that couple will be W sin theta into distance between them, that is L. So W sin theta into L. So suppose I am taking it is a negative sign. So to balance this the couple, there must be another couple. It is inertia couple. So that couple I'm seeing as I into theta double dot, I into theta double dot. So that couple I'm saying is I into theta double dot. Now how this I into theta double dot came? So the formula for force, as we know in linear systems, so linear system, the formula for force is F is equal to ma. So similarly in rotary motions, so in rotary motions we use the formula for couple. So here couple is nothing but we can say as a torque. So the formula for torque will be, so instead of mass we use I, that is moment of inertia, and instead of acceleration we use angular acceleration, that is alpha. So here as we know that m is x double dot, so here similarly I can write alpha is equal to theta double dot, because as we know that acceleration is the second derivative of distance, and similarly acceleration angular will be the second derivative of the angle. So similarly, so now we will write the formula, that is I theta double dot is equal to minus W sin theta into L. So if I further uh, bring this component on the right, so I will get I theta double dot plus W sin theta L equal to 0. Now let's divide the whole equation, dividing the whole equation by I, divide by I. So I will get theta double dot plus W sin theta. Now what is W? So instead of W I can write mg, mass into gravitational acceleration. So that is mg sin theta L upon I is equal to 0. Now when theta is very small, so as we know that when theta is very small, we can write as sin theta is equal to nearly equal to theta. So here we'll write instead of sin theta as theta. So we'll get theta double dot plus mgl upon I theta is equal to 0. Now we'll compare this equation with SHM. So as we know that SHM equation is that x double dot plus omega n square into x. So the natural frequency after comparing with SHM, we will get omega n square is equal to mgl upon I. So omega n would be equal to under root mgl upon I. Now what is I? So I is moment of inertia. So what is the formula of moment of inertia? So as we know that the formula of moment of inertia is mk square, that is m mass into radius of gyration. So radius of gyration is just distance between the center of the axis of rotation to the radius. So here that k is nothing but l. So here I can write it as mgl upon mk square. So mm get cancel, sorry, ml square. Here k is l, so ml square. So mm get cancel, ll get cancel. So omega n will be equal to under root g by l. So now if I want to write it as a linear frequency, so fn is equal to 1 upon 2 pi under root g by l. So this is the form of linear frequency, and this is the form of angular frequency. So this is we have solved with the help of equilibrium method, or we can say it as Newton's method. But now we will use the another method, that is energy method, to solve the same, to find the same equation. So we'll use energy method to solve the same equation and to derive the result. So so in this case I will again draw the diagram, that is pendulum, simple pendulum. So a bob, a string, a string, and suppose it is having a mass m and is extending an angle theta. So here the for energy method we need to find kinetic energy and potential energy of the system, and then what we are doing, that we are summing the both the energies and differentiating it uh, and equating it to the zero. So we will get the formula for the equation of motion. So here what is the kinetic energy? So kinetic energy, as we know, in linear system we use 1 half mv square. So here for rotary system we will use the formula of kinetic energy is 1 half, instead of mass there will be moment of inertia I, and v instead of velocity we will use theta dot square. So this is called angular velocity, that is theta dot square. So here for potential energy, the formula of potential energy is mgh, it is mass into gradation acceleration into height. So what is height here? So height is nothing but the difference between the equilibrium position and the current position or the extreme position. So here the distance between this and this will be height h. So this is h. Okay, so how I will find this height h? So suppose this is the length l and this is also the length l. So what will be, so here we need to find the value of h. So how we can find h? So suppose I am redrawing this diagram. So suppose this is the length l and suppose this is extended and this is angle theta and this length is also l. So I want to find this length h. So what I will do is I will just extend a line which will extend 90 degree to this angle. So here as we can see that alternate angles are created, so this angle will be also theta. So now if I can find this length, what is this length, then I can find the value of h. So what will be this length? So here it is l, so this will be l sine theta and this would be l cos theta. So now I got the total length is l and if I subtract from this total length this length L cos theta, so I will get the length h, because the total length is h plus L cos theta, that is L. So h I have got, that is L minus L cos theta. So potential energy will be equal to mg L into 1 minus cos theta. So I have got kinetic energy, I have got potential energy. So now what I will do is the total energy U, as we know that it is kinetic energy plus potential energy. So that will be equal to 1 by 2 I theta dot square plus potential energy mgl into 1 minus cos theta, that is U, total energy. So if I want to find the equation of motion, so similarly what I have done in energy method, the same thing I will do here again. That, as we know that total energy is constant, so if I differentiate any constant, so the result will be 0. So differentiating du by dt is equal to, so if I differentiate, so what I will get is 1 by 2 is the constant, so it will come out. Then I is also a constant, so it will come out. So differentiation of theta dot square, so 2 will come out, so into 2 into theta dot raised to 2 minus 1 will be 1 to theta dot, and the differentiation of theta dot again will be theta double dot, plus m is constant, g is constant, L is constant. So differentiation of 1 will be 0, and differentiation of cos minus cos theta will be again minus sin theta, so minus minus will be plus sin theta. And the according to chain rule, so we have to also differentiate theta, so differentiation of theta will be theta dot. So so this differentiation of total energy with respect to time will be equal to 0. And here if I simplify this equation, then 2 will get cancelled, and theta dot will come out as a common, and this theta dot, if I bring on the left hand side, it will merge into 0. So what I'm left with is I theta double dot plus m g L sin theta. So theta dot is gone. So the same equation I have obtained, which I have obtained with the equilibrium method. So the same equation I will now just divide the whole equation with respect to I. So I will get theta double dot plus mgl upon I sin theta is equal to 0. The same again we will write when theta is very small. So we can write sin theta is equal to theta. So we can write mg Li theta equal to 0. Now if we compare this with SHM, so we'll get omega n will be equal to under root mgl upon I. Now what is moment of inertia? That is mk square, and here radius of gyration is length, so we'll get mgl upon ml square. So L cancel, cancel, so we have got the natural frequency as under root g by L. So if I want to write in the form of linear frequency, we will write 1 upon 2 pi under root g by L. So the same equation we have obtained with the help of energy method also. So in exam, it may be possible that you it is written that solve or find the natural frequency of the system, and system is given in the form of diagram, and by using energy method or equilibrium method it can be written. So in that case you need to find with any of this method. So I hope you understand both the method. So we will take one more example in the next lecture, but now I will just introduce a small topic, that is springs, equivalent springs. I can write equivalent springs. Sorry, equivalent springs. So what is equivalent springs? So suppose there may be case that there are two springs in parallel conditions. So this may be case that a mass m is attached with two springs having stiffness k1 and k2, and here the force, that is weight, is acting in downward direction, that is mg. And there might be also possible that the springs are in series. So this is the first case. Let us discuss this as springs in parallel. So now what we can see that we can see that this spring we can also describe in this condition that two springs are attached in such a fashion that they are in opposite directions. So in this also we can say that this are in parallel condition. So because this both fixed points can be merged. So this spring, equivalent spring, we need to find if I want to just use one spring. If I want to use just one spring, that is spring with stiffness K having the same mass, so what will the value of that K? If instead of two spring, if I want to use just one spring, so what will be the K? So suppose let's see this diagram. So suppose the total weight W is mg. So let W is equal to W1 plus W2. So that is the half of the weight is carried by this spring, and another half, not means totally half, means some of the weight is carried with this spring and other weight is carried by this spring. So I can also write m is equal to m1 plus m2, because g is constant, so g will get cancelled out. So suppose this spring is moving in downward direction and having some displacement, say y. So suppose this spring is moving in downward direction and having some displacement y. So the displacement of both this total will be the same. That is, suppose that displacement is y. So if I want to write the equation, as we know that force is equal to ky. So what will the y is equal to f by k. You can write f by k. So here f force is, that is weight of the uh, bob, that is mg. So I can write y is mg by k. So this displacement is same. So here I can write it as, it is mg by k is equal to m1g by k, m1 m1g by k1 is equal to m2g by k2, because the displacement of this spring and this spring will be the same, and the displacement of the equivalent spring will be the same. So if I cancel out g, so what I'm left with is that m by k is equal to m1 by k plus m2 by k. So if I use this same formula here, so what I will get is, so let's use the same formula. So what we'll get is, suppose I can write m1 is equal to uh, m into k1 by k, and m2 is equal to m k2 by k. So m1 and m2, if we use this in this formula, so what I will get is m is equal to m1 plus m2, as we know. So I can write m k1 upon k plus m k2 upon k. So m gets cancelled. So we are left with, if I take this k on the left side, k is equal to k1 plus k2. So when the springs are in parallel, so the stiffness gets just added. And similarly, as we know, this equivalent this system is equivalent to electrical circuit, the parallel and series. So if we have got this result in parallel, that is k is equal to k1 plus k2, so what result we will get in series, that is 1 upon k is equal to 1 upon k1 plus 1 upon k2. So we'll discuss that second case, that is springs in series. So in this case, if there are two springs having k1 and k2 and mass m, so here the deflection of the spring 1 and spring 2 will be different. That is that y will be equal to y1 plus y2. So what is the formula for y? So the formula for y is mg by k. So let's write mg by k1 plus mg by k2. So suppose the equivalent spring stiffness is k, so it will be mg by k. So mg gets cancelled, so we'll get 1 upon k is equal to 1 upon k1 plus 1 upon k2. So we'll just see one example based on this, which was asked in exam. So suppose an example is given, let's solve based on this equations only, that so there are three springs in parallel having stiffness k1, k2 and k3 having mass m, and there are two springs in parallel in opposite direction, that is k4 and k5, and here it is fixed support. So the value of k1 is given as 2800 Newton per meter. K2 is given 1400 Newton per meter. K3 is given 1900 Newton per meter. K4 is given 400 Newton per meter. K5 is given 400 Newton per meter, and the value of mass m is given 0.5 kg. So we want to find angular frequency, that is omega n. So we need to find angular frequency omega n. So to find omega n, we know that the formula for omega n is under root k by m. So we have the value of m. We need to find the equivalent stiffness k. So for that k, we need to solve this whole and equivalent spring stiffness k. So we'll start with these two are in parallel. So as we know that for parallel, we need to just add these equations. So k parallel will be equal to k4 plus k5. So what is k4 and k5 is 400 plus 400, so it will be 800 Newton per meter, and these are in series. So what will be the formula for series? So k series is 1 upon k series is equal to 1 upon k1 plus 1 upon k2 plus 1 upon k3. So what will be it? 1 upon 2800 plus 1 upon 1400 plus 1 upon 1900. Sorry, the k3 value was 700, so I'll just take 700. So taking LCM, so 7 4 ja 28 and 14, I think 2 ja 28. So it will be 1 plus 2 plus 4 divided by 2800 1 upon k series. So k series will be 2800 divided by 4 5 6 7. So 7 4s I guess, so it will be 400. So what will be our equivalent spring stiffness? So still we have not got the equivalent spring stiffness, but we have got the k parallel is equal to, we have got k parallel as 800, and k series we have got 400 Newton per meter. So now what condition these two springs are now? So this is also a case of parallel. So the equivalent spring stiffness k will be k series plus k parallel, so that is 400 plus 800, so that is 1200 Newton per meter. But still our example has not been solved. So what is the formula? We need to find the natural frequency, so that is omega is under root k by m. So what is k? K is 1200, and what is m? So m is 0.5 kg, so that is 0.5 kg. So if I need to solve this equation, 1200 divided by 0.5, what is 0.5 is 1 by 2, so it will be into 2, so that is 2400 under root. So I can write it as 10 root 24, and 24 I can write it as, so 24 I can write it as 6 4 ja 24, so 4 can come out, so 20 root 6. So that is the natural frequency. If I want to find the linear frequency, so it will be 1 upon 2 pi 20 root 6, so it will be 10 root 6 by pi for linear frequency. So this solves our example. So we'll see few examples also in next lecture. So thank you very much.